Any of you guys taking any other math courses besides this one? Like this semester? And if so, what are you taking? CSCI 160? What is that? I don't know what CSCI 160 is. Discrete math. Okay, yeah, I know discrete math. That class is about well, I don't know. It's about discrete math. It's using comp sci. It's a lot of Boolean algebra. Okay. Count stats. Yeah, I would count stats as part of being math. Stat 213. I like that course. Stat 213 was a good course. Well, actually, the goodness of a course depends on the professor, I feel like. But I did enjoy the material in that course. Three hours on a Saturday afternoon. Yeah, a lot of the stats 1-3 sections are on Saturday afternoons, which actually when I took stat 2-3, it was on a Saturday afternoon. It was fine, in my opinion. Discrete math has more critical thinking. Yeah, I mean, I don't know if you like that more. I do prefer classes that make you think more. Because I don't know, I feel like just learning formulas and using them is kind of mindless. You know what? To me, like nothing even feels like a weekend. Like every day is the same. There's no such thing as a weekend. That's why I didn't mind. Okay, let's go over this question. So first question is, which trig function did you guys decide to split? Sine? Okay, I guess we can split sine. Anyone else try to split the other one? Anyone else try to split cosine instead? No, everyone did sine. Um, okay, I'm not talking about the u substitution yet. I'm talking about when you rewrite this function, what are you splitting? So if you're splitting sine, I'm assuming you rewrote sine cubed as sine squared times sine to the first power. But I'm assuming no one split cosine, right? Okay, then in that case, let's just stick with sine. So let's begin. So this is sine squared of x times sine to the first power of x times cosine to the fifth of x dx. Okay, so the reason we did this is because we're trying to get um, something to the first power, right? Because that'll leave space for du. So our plan is to leave leave this along with this, to be du, which means everything else needs to be in terms of cosine. So the cosine to the fifth power is fine because that's already in terms of cosine. But we need to rewrite sine squared to also be in terms of cosine. So that's 1 minus cosine. And then we have cosine to the fifth of x. And then here we're going to have sine of x dx. All right. So at this step, we can go ahead and do our u substitution. So this will be u equals cosine of x. So du is negative sine. So if you were to substitute it, you get 1 minus u squared. This is u to the fifth. So here we have sine of x dx, but our du is negative sine of x dx. So we're going to have to write du, and then we're going to have to make it negative to account for this negative. All right. And then at this point, I think you guys can pretty much figure this out. So you can just expand this. So this is u to the fifth minus u to the 7 du. And then when you integrate, you get u to the 6 over 6 minus u to the 8 over 8 plus c. And then we just need to substitute what u was. So that was cosine. So this is negative cosine to the 6 minus cosine to the 8. Okay. Any questions on that?
How'd you get u to the seventh power?
So I multiplied the u to the fifth. I distributed inside both terms inside the parentheses.
Oh, I see it now.
So yeah. Okay. So for this question, we were able to do it by splitting the sine part. I guess I have a question. Could we have done this problem by splitting cosine? What do you guys think?
Yeah, I think we could have.
Yeah, probably, right? Why can we for this question?
Because we could have cosine to the fifth could be split into like cosine to the fourth and cosine x, and then those things would cancel out because we know the derivative of sine is cosine x. So we know that those things will be replaced in the future.
Yeah, because well, the cosine to the fourth and then the cosine to the first. The cosine to the first will be left for like the du part, but we could rewrite cosine to the fourth to be in terms of sine, right?
Yeah.
Yeah, so that's really the reason why we also could have split cosine if we want to. But let us revisit the previous questions we did to take a look at them a little deeper. So we just did that one. So for this one, we established that we could split either function. This one we did yesterday. Do you guys remember which one we split for this one? Not yesterday.
We split sine.
Tuesday. We split sine. Okay. Did we try splitting cosine?
No,
No. Why would it? Did it not work, or did we just not try it?
we just didn't try it.
Okay.
But it would work. I think it would. Because you could have split into cosine squared and cosine squared.
I don't think this would work because don't we need cosine x in the end?
Yeah. Because if you've noticed from these three problems we did, like we did 3 of these so far, every time we split one of the trig functions, we need something to the first power in the end always, because that's left for the du part of the u substitution. So for this one right here, I mean, you could split it into cosine squared and cosine squared, but that wouldn't, I don't think that would work because you don't have anything to the first power. Do you guys see what I'm saying?
Yeah, I get what you're saying.
So that's why for this question, example 2, this one, we had to split sine because that's the only one that would have left something to the first power in the end. And if we split cosine to say like 1 part to the third power and 1 part to the first power, that wouldn't work either because the third power, the one that's cubed, wouldn't be able to, we can't write that in terms of sine because the trig identity is in powers of 2, like cosine squared. So, and then there was this example. This was the very first one we did. Which one did we split here?
I think cosine.
Yeah, I think we split cosine here too. So for this one, we split cosine. Example 2, we split sine. The one we did this now. We could have split both. Well, we could have split either one. So, do you guys see a pattern here or no? Like, what is the condition that allows us to be able to split it?
I notice we're splitting the ones who have an odd number as in power, not an even number.
Yeah. I think that's really the key here. So if you have a trig function, like for example, like sine and cosine, and they have powers, you want to split one with the odd power. I think that should do it. Yeah, so for this one, we split cosine because it was odd. And then for this one, we split sine. And then this one, we could split either one. Okay, so, oh yeah, this is just what we were talking about. Regarding the x1, so how does the degree parity, so parity means like if something is even or odd, of the cosine and sine functions, how does that affect the integral process? Someone walked away for a moment. Okay, so can someone just like restate what we just said? Maybe in their own words. So when dealing with integrals of sine and cosine functions, which one do we split and why?
We split the one where the exponent is odd if the other one is even. So it could easily cancel out. Oh, the explanation is bad.
Well, no, you were fine. It's just when you say cancel out, that's a little bit vague.
Yeah,
It's like,
I know.
why does it cancel out?
Because it's a smaller term and it's when you take a derivative of it. it will probably cancel out at the end since there'll be two small terms together. It's still vague.
Yeah, it's not always a smaller exponent, because if you look at example 1, we split cosine, and cosine was not the one with the smaller exponent.
I think you that you can use like some kind of a trick property to convert the cosine back to a sine.
Yeah, that's really the main idea here. So whenever something has an odd power, you want to split that one, because the odd power can be rewritten as something to the first power times another part to an even power, and then the even part can always be rewritten as the other trig function. Okay. If they're both odd, so we established here that if they're both odd, you can split either one. But it's probably easier just to do the smaller one. Yeah. Okay, so that's the conclusion for these questions. Let's see. Okay, so here we have an example where both exponents are even. So I guess we're screwed here. Well, this is the next example, so let's try doing it. So this is integral of sine squared of x times cosine squared of x. I'm gonna let you guys try this for just a little bit. So I'm gonna give you guys 3 minutes, but before you start, let me just tell you a few things about this question. It's not gonna be the same process as the previous 3 we did, and you're gonna need different trig identities for this one, okay? So just try it for 3 minutes. It's okay if you don't get it, but it's worth a shot, so go ahead. Make sure to have your trig identity sheet out. Okay, while everyone's doing that question, I'm going to try to address the question that Queenie just wrote. So the previous question was, so Queenie, this is for you. It was sine 3 of x times cosine 5 of x. So we split sine, but we can also split cosine. And the reason why is because we can write it like this. Sine 3 of x times cosine to the 4th of x times cosine of x. This is sine to 3 of x. And then cosine to the 4th power can be rewritten as cosine squared of x squared times cosine of x. And then we can turn cosine squared of x into 1 minus sine squared of x. Okay, so this is why we can also split cosine, is because from this process, we can let u equals sine of x. And then du will be cosine of x. Okay. So this is the illustration that we can split either sine or cosine as long as the thing we're splitting has a odd power. Okay, so did anyone make progress in this question? Not much. That's okay. Isn't there a trig identity for sine of x? Wait, what did you just write? Oh, sine. Are you trying to write squared? Yeah, okay. Probably. I don't know. Maybe not. If there is, let me just look at the trig identity sheet. Sine squared of x times cosine squared of x. No, I don't see one. No, I don't think there's an identity for that.
I think there is. It's like sine 2x equals 2 sine x cosine x.
Say that one more time. I'm gonna write it down.
Sine 2x
Sine 2x
equals 2
to
sine x cosine x.
sine x cosine x. Okay, well that identity doesn't have the squared in it, so
Well, you could rewrite the original one as sine cosine x and then to the power squared. I think
okay.
that's what they did.
Yeah, okay, yeah. We can do that. So rewriting the original question, you can write it as sine of x cosine of x, the whole thing squared. And then we can substitute what I just wrote inside the parentheses because it's basically this part here, just without the 2. So let me just move the 2 over. One half. So now using the identity, we get 1/2 sine of 2x squared. Okay, great. I feel like we made progress. I guess we'll square it. So if you square it, you will get 1/4 sine squared of 2x. All right. Any idea what we can do now?
Maybe rewrite sine squared in terms of 1 minus cosine squared x. But then the 2x, I don't know what to do with that.
Yeah, I mean, we could do that, but I don't think that would help because there's still like a square there, and then there's still a 2x. So it doesn't really make it simpler. One tip we can use is that whenever you have a trig function that's squared, consider using the power reducing trig identities, because those help you get rid of the powers. So I think there was one. Does anyone remember the power reducing ones? All right, let me look at it. Okay, here they are. So let's try using one of these. Which one do we need? We need this, the one for sine, so that's the first one. So if we were to use the first power reducing identity, what will our what will it become? Can someone tell me?
1 minus cosine 4x. Since we're 2
Yes, 4x.
divided by 2.
Yeah. Okay. So notice how in the formula, if your input is u, then after you apply the formula, it turns into 2u. So in our case, our original input was 2x, so we changed it to 4x. Okay. All right. So I'm going to factor out the 2 in the denominator. So that's 1 over 8. And then 1 minus cosine of 4x dx. All right, at this step, we should know how to do this. So the 1/8 can stay there. The integral of 1 is just x minus, what's the integral of cosine of 4x?
Would it be negative sine 4x times 1 over 4?
Yes.
Negative 1 over 4 sine 4x.
Like this, right?
Yeah.
Yeah. Okay. Yeah, there you go. So that's your answer. Okay, so we were able to do this problem. This one required 2 trig identities, right? It required this one as well as power reducing one. So you can see how the identities are pretty important. Is everyone okay with that? All right, so that's an example where the exponents were both even, which made the question a little more harder. So if one of the exponents are odd, you can just do it how we did the previous 3 questions. If they're even, then it's like this. What's next? All right, so now we move on to an example that is not just sine and cosine, but this one has cosine and tangent. So Let's see if we can try this one. Actually, let's do this one together. So just take a moment to copy it down. Okay, so cosine square root of x times tangent to the cube of x. We're gonna see if we can do it together. So let's try to figure this out. Just looking at this question, does anyone have a suggestion as to what we can do first?
We write tangent as sine over cosine.
Yeah, that's what I was thinking too. So if we do that, this will be cosine square root of x. Tangent is sine over cosine. So like this. Okay, and then some cosines cancel out, right? So we will be left with 1 cosine in the denominator. All right, I feel like that's good so far. What can we do now?
Split apart sine cubed into sine squared and sine.
Yeah, okay. Let's see where that gets us. Sine squared of x times sine of x over cosine of x dx. Okay. Now what? I think I could see a good next step, but I'm gonna give everyone a chance to see if anyone else have any suggestions.
You can make u sine of x and then find du.
If you make u sine of x, so let me write that down. If u is sine of x, then du is cosine of x, right?
Yeah.
Now, I only have one issue with this suggestion. The fact that du is cosine is no problem because we do have a cosine. The only issue here is that cosine is in the denominator. That's the issue. So because it's in the denominator, we cannot just like call this entire part du. So I would probably suggest something else.
Can we change sine squared x to 1 minus cosine squared x, or would it not work?
You can. That's what I was thinking, actually. That was what I thought would probably be the right choice. So if we were to rewrite sine squared of x as in terms of cosine, then we would have 1 minus cosine square root of x times sine of x over cosine x dx. So does everyone see where this question is going now? You can actually just do your u substitution now. So who wants to fill in the u and the du?
Would u be cosine of x, and then du is negative sine x?
Yeah. So everyone notice how you have a sine x of dx here. So that's probably going to be the du. So that means u has to be cosine. So this is negative sine of x dx. So now this becomes 1 minus u squared over u. And then sine of x dx is du, but without the negative sign. Okay. All right, and then this should be something we can integrate. So we can rewrite this as 1 over u minus u squared over u, right? That's the same thing. So then rewriting again, this is u to the negative 1 power. And then this is, actually we didn't even need to rewrite that. This part is just u du. So integral of 1 over u, do you guys remember what that is?
ln of u?
Yeah. Minus integral of u is u squared over 2. Okay. Plus c. And then let's just put back what u was. So u was cosine. So negative ln cosine x minus cosine squared of x. Okay, so there's your answer. So Devin, I see your suggestion as to rewriting tangent at this step. You can do that, but I don't think it would be a good choice because our original question started with tangent. So it really wouldn't do us any favors to go back to tangent. So that's why I wouldn't recommend that. Usually we like things that are in terms of sine and cosine. Okay, so
Can
this
you
one,
scroll up?
yeah. Did someone want to say something?
Yeah, can you scroll up a little bit?
Yeah. So this one didn't really require any identities, which is good.
Can I just see the last part of the final answer at the bottom?
So what do you think about these kind of questions so far? This whole section of trig integrals. If we have problems like this one, do we always split up the tangent? I mean, yeah, I wouldn't say always. A good rule of thumb would be to rewrite everything in terms of sine and cosine, but also consider trig identities.
Professor, I had a quick question. So if you can scroll up a little bit really quickly.
Mhm.
So remember how you said that using sine of x as u would not be good? So like, can you repeat why it wouldn't be like in this initial step? And if we were to have done it, would we still end up with the same answer, or would we just not get an answer at all?
Yeah, I'll explain that again. So going back to this step here, we wanted to, well, we wanted to see what would happen if we let u equal sine of x. And if we chose to do that, then du is cosine of x dx, right? Now, the reason why this was not good is because even though we have a cosine of x dx in our integral, the cosine of x is in the denominator. So because it's in the denominator, we don't have anything for du basically. That was the issue. Only if cosine of x was in the numerator could we have replaced it with du. But because it's down here, then this substitution does not work.
Okay, I see.
Yeah, so we wouldn't get an answer at all.
Okay, thank you so much.
All right. Yeah, I'll be honest. I don't really like the questions here. They're kind of tedious. But then again, like I think every section is tedious. Do we use this in the real world? No, I'm sorry. You're never gonna use anything you learn here in the real world. I know it's a shame. You know what? Like the stuff we learn in math, like half of it is just theory. Like we're still like as we move towards like the future, like people just find new applications of different topics in math. Like people use it from physics and stuff. Okay, we have one last question, and then that'll be the end of the section. So why don't we take a look at the last one? Here we go. Yeah, you could have turned it into cosine to -1, but that still doesn't make it du because du is cosine like in the numerator. Whoops. So example 6, let's do this together.
I have a question.
Mhm.
Does the 13 apply only to tan or both tan and secant?
It's just like 3 things multiplied together. So it's 13 times 10 to the 4th x times 10 times secant to the 6th x.
Okay.
So yeah, it's like 3 products. You could just bring the 13 out of the integral as your first step. All right, so let's see how we can solve this one. So our first option is to convert everything in terms of sine and cosine. We can do that, but there's actually something, there's actually a trig identity that, if you recall, will make this question doable without turning everything in terms of sine and cosine. So do you remember the Pythagorean identity for tangent and secant?
One plus tangent squared equals secant squared.
Yes. So we can actually use this identity to do this question similar to how we do like the ones where you split the sine and cosine stuff. So how should we split this? Also, you guys remember what the derivative of tangent is, right? D dx of tan of x.
Secant squared x.
Yeah. So that might come in handy as well. So how can we do this? Any ideas?
Rewrite secant to the 6th power as 1 plus tan squared x to the power of 3 as a whole, maybe.
Well, if you do that, then everything's in sort of tangent, right?
Yeah.
So I don't think we want that, because if everything is is the same trig function, then you have nothing for du, right?
Oh, okay.
I do think we could split secant of 6x, but not in the way that you suggested, but just in a slightly different way.
Maybe as 4 and 2, secant to the power
Yeah,
of 4 and
I
secant
think
of 4.
that's probably good. Tan 4x, secant 4x, and then another secant of 2x. So does anyone see why this is good?
Because if we take u for tangent 4x, we could easily take the derivative and it'll cancel out.
Yeah, so everyone notice how this secant squared x dx right here, this is the derivative of tangent. So that can possibly be our du, right? So if we want that to be our du, then we have to turn everything else to be in terms of tangent. So this is fine, but can we turn this to be in terms of tangent?
Would it be 1 plus tan squared x to the power of 2?
Yeah. So it's like this. Secant squared. Let me just write a middle step here. Secant to the 4th of x is technically secant squared of x squared. And then secant squared of x is 1 plus tan squared of x. Okay. All right. So now we can do our substitution. Tan of x. So du is secant squared of x dx. (13) u to the 4th 1 plus u squared du. Okay. U to the 4th 1 plus u squared squared. I think I remember how to do this. So it was like 1 times 1, I think. It's like 1 plus. How do you do this again?
2u squared plus u to the power 4.
No, wait, there was supposed to be something more than that. So I guess I'll write it out. 1 plus u squared times 1 plus u squared.
Foil.
Yeah, I forgot what that meant. So it's, I know you do this first, 1 times 1.
Yeah.
And then
1 times u squared and 1 times u squared, which is 2u squared. And then u squared times.
so yeah, something like that. 2u squared. And then what was it?
U to the power 4.
Okay. All right. Du. So then I can distribute the u to the 4th. So this is u to the 4th plus 2u to the 6th plus u to the 8th. Wait, yeah, that's fine. We haven't integrated yet, so this is fine. Now we integrate. So this is 13 u to the 5 over 5 plus 2u to the 7 over 7 plus u to the 9 over 9. Okay, and then we just put what u was back in, which was tangent. So 13 tan 2 tan to the 7 Okay, so that's that. Any questions? So are we all good? All right. Let me just switch back to the PowerPoint. So at this point, you have enough knowledge to do homework 6.2. So do try that on your free time. It's integrals involving trig functions. There are a lot of different scenarios that these questions take. So some of them will probably be stuff that are not similar to anything during lecture. But unfortunately, we don't have time to cover all the scenarios. So the next slide, I have some advice for you guys when doing these problems. our exam is going to be in 2 lectures. So next lecture, we're gonna go through a review sheet that I'll send probably tomorrow or Saturday. And yeah, so here's some advice that I have for you guys. Specifically for this section, do have your trig identities sheet ready when doing the problems because you'll need it. And there's going to be a lot of different scenarios that these problems can take. So the more complicated a problem is, the more ways there are to doing it. So you do have to be creative with these problems and don't just give up like when you can't do it after 5 seconds, right? Oh yeah, by the way, that comment about someone saying how, are we gonna ever use any of these in real life? No, I've never used anything I've learned in Cal2 in real life. But what I have learned is that these math courses, they teach you how to solve problems, okay? So that's really what I learned from taking math, is to be able to just like persevere and solve a problem. Yeah, so also work together if you guys can, because if someone else, or if you don't know how to do a problem, chances are someone else might. And then the last advice I have is this website called symbollab.com. Has any of you guys ever heard of that? No, yes, yes. Who hasn't? Yeah, I mean, it's similar to like, there's other websites like it, like Wolfram Alpha or whatever. But what it is, for those of you who hasn't heard of it, it does your math problem for you. So let me just give you guys an example. Here it is. Let's say we want to do the integral of, I don't know, what did we do today? Sine squared of x times cosine squared of x. And then you press it and it tells you pretty much all the steps that you need. So it says use this identity, so on and so on. So yeah, for those of you guys who've never seen it, you're probably blown away right now. But
Yeah.
yeah, I would recommend you using this website to not necessarily do the problems for you, but after you try a problem, you can use this to see if you did it correctly. So yeah, I don't recommend you just like plugging into the problem right away without like doing it, because then you're not learning anything. But yeah, so this is a resource that I would recommend if you're really, really having trouble and like you really have nowhere else to go. Yeah, I know they sort of like hide the steps now, but I think they still show some of the steps. Like they over here, they show you what identity to use. So it's still useful. Yeah, I'm sure there's other resources too. Okay, so that's all the advice I have. I'll send out the review sheet for the exam sometime tomorrow or the day after. And yeah, that's it for today. So I will see you guys next Thursday. Yeah, exam is October 6th.
Are all the homeworks due October 6th or October
Yeah,
1st?
I'll set them to be due October 6th because that's when the exam is.
Okay, thank you.
Professor, is the review sheet going to be similar to the exam format?
Yeah, I'll try to make it as similar as possible.
Okay, thank you.
Will the test be open the whole day or during class? It'll be during class. Yeah.
I have a question. Since there's all the classes are since Tuesdays and stuff, what is the exact?
I'm sorry, you cut out there. Can you repeat your question?
What is the exact test date? Because we said there were some changes.
Yeah, so September 29th, which is a Tuesday, runs on a Monday schedule, so we're not meeting on that day. And then October 1st, we'll review for the exam. And then October 6th, we'll take the exam.
Oh, all right, got it. Thank you.
Raymond, we do not have class next Tuesday.
Professor, will you be offering office hours in the upcoming week for practice for the exam?
Well, because we don't have class on Tuesday, yeah, you know what? Yeah, I'll still hold my office hours next Tuesday.
Okay.
Yeah, so if you would like to come, then just send me an email.
Thank you. Okay. Have a good day.
Yep, you too.